Comes on here. Let's start off. Let's go ahead with the problem. We got a ring of radius r. On the axial line, there is a smaller ring. It's a smaller ring of radius smaller. R is much greater than r. So this big loop is much larger, and at the axial line, you kept a small loop at an angle theta as shown. Find the torque and the force on the small loop due to the big one. So till now we have seen interaction between wires and wires, so it is a loop and loop now. The big loop is much larger than the small one. How do you find the force and the torque? What is torque? Remember mu cross B. So B is the external field. So due to the big one, the magnetic field at this thing so that will be mu naught I r square by 2 times r square plus x square whole power 3 by 2. Torque is nothing but mu cross B. Mu is due to the small coil. B is the external field, that is the big coil. Torque mu is NIA, N is 1, I area will be pi r square into B sine theta. That substitute the values, you'll get it. Torque is fine. What about the force? How do you find the force? The only formula we know about force is I dl cross B. But here, the whole, that small loop is also at an angle. The B is also, I know, only B on the axial line. I know we encountered a problem like this in capacitors. Force on a dielectric slab. Did anyone remember what we did? I don't know how to find force directly, but I know how to find potential energy. Potential energy U is equal to minus mu bar dot B bar. So potential energy will be minus mu will be I pi r square into B. What is the force relation between force and potential energy? Minus du by dx. That will be I into pi r square dB by dx, which is I pi r square dB by dx will be mu naught I r square by 2 r square plus x square whole power 5 by 2 into 3x. Just differentiate this quantity dV by dx. Clear with that? So remember that even if you remember in capacitors, right, that was the technique every time. If you give me something weird, I can't find the force directly, but I can find the potential energy as function of x, du by dx. Clear with that? So that is how you can find forces and torques between two loops. Any doubts on this? Next one. Clear, everyone? Aditya, Puroja, Pushkal, Vivan? We have an infinite charged cylinder. So this entire cylinder has charge on the surface. Sigma is the surface charge density. Now you started rotating the cylinder by omega. Find the magnetic field inside. This is something I kept on telling you from last few classes. If a charge rotates in a circle, it behaves like a current loop. If there is a current loop, there's a magnetic field. In last class, the question we did, if you remember, an infinite sheet was moving, it behaved like a current sheet. Infinite charge sheet moving with speed, we behaved like a current sheet. So what does this behave like? Find the B inside the cylinder. Think it's a good one. These are the kind of questions they'll ask you, like, they'll give you charges and they'll ask you for field, and most people will get confused, like, how do you convert that? You get me the answer, Naditya. Exam, whom will you go and ask? Get a wrong answer at least, then we'll see. This thing behaves like what? An infinite solenoid. So if you consider an infinite solenoid, which is carrying current I, so here also you can think of something like that. when this is rotating, we have a lot of, each ring is behaving like a current. So the field due to a solenoid is mu naught small n I. This can be written as mu naught capital N I by L. N is the total number of turns. And N into I will be the total current. That means I can write this thing as mu naught I total by length L. So for this solenoid, the total current will be the total charge by time. The total charge will be sigma into 2 pi r L. Surface area by time will be 2 pi by omega. Sigma omega r L. This will be mu naught sigma r omega. That's a magnetic field, everyone. So a rotating hollow cylinder behaves like as kind of like a solenoid, a tightly wound solenoid. So that each ring behaves like one current loop, and when you add all of them, you get this. Clear with this? Right, Vihan. So this is important. So when they give you some kind of a charge and something, and they ask you magnetic fields. You need to understand whenever a charge moves, it behaves like a current loop, and that thing gives you a magnetic field. Clear with this? Yeah, that's a bit about different shapes that we did. The next thing that we have, so whatever we did so far is all using Biot-Savart law. We used integration and everything. We also have a concept called an Ampere's law, just like we had it in Gauss law and Coulomb's law. Coulomb's law is like Biot-Savart's law, and Gauss law is like Ampere's law. So Ampere's law is useful to find magnetic field for symmetrical current distributions. So let's see. We will also derive this thing using Biot-Savart's law. So what Ampere's law says is, again, initially this was done experimentally. The line integral of magnetic field over a closed loop is equal to mu naught times the current crossing the loop. So what this means is, if you take any random loop, and let's say there's a current wire I here, and let's say this thing is giving a magnetic field B here, B here, and if you take DL will be along the loop. So if you integrate, line integral meaning, so integral B bar dot DL. So for every segment, integrate B dot DL, and if you add all of them, he's saying this will become equal to mu naught I, where I is the current crossing the loop. This is your Ampere's law. If you remember in Gauss law, it was integral E dot dA is equal to Q enclosed by epsilon. But here it is a line integral. So that means you're integrating with a length. In Gauss law, you're integrating with surface integral, that was. This is valid for steady currents. Steady currents meaning currents that don't change with time. If currents change with time, that will create a time varying magnetic fields. A time varying magnetic fields will create electric fields, and the whole thing will start getting messed up actually. Right now, we'll not get into that, but we do have that. So this Ampere's law, right? It goes wrong when the currents are changing with time. So we study that in electromagnetic waves, modified Ampere's law. But for now, let's see this thing. And I hope you know the meaning of this integral symbol. The meaning of this integral is a closed integral, means you're integrating over a closed loop. In Gauss law, it was integration over a closed surface. So that circle indicates you're integrating over a loop. We will try to prove this. But again, this was initially experimentally was derived this way. So let me give an example. So if you got a loop, let's say there are multiple wires, I1, I2, I3, and I4. What this Ampere loop law says is integral B dot dl will be mu naught I crossing, just like Gauss law. In Gauss law, remember what was E? E is the field due to all charges inside and outside. Similarly, here also the magnetic field B is due to all wires. So here B bar is B1, B2, B3, and B4. So I crossing here will be only I1 minus I2. So the loops outside will not create any B dot dl. The summation will be 0 basically. So here you will hear some terminologies. Ampere loop. This is something you'll hear, just like Gaussian surface. What's a Gaussian surface? It's a closed surface on which electric flux is calculated. What is an Ampere loop? Ampere loop is a loop on which integral B dot dl is calculated. So what is the primary application of this? Ampere law is useful to find magnetic field due to symmetrical current distributions. If there is a symmetrical current distribution, you can use Ampere's law. If it is not symmetrical, it's not that useful. If you remember, the idea was similar to Gauss law. Gauss law was useful to find electric field due to symmetrical charge distributions. There, so this is an example for the Ampere law. So if you give me a loop and if you have some 10 wires, and if you calculate the magnetic field due to all the wires and do B dot dl, the summation will be mu naught times the current crossing. Let's see how this comes out. This is important. What if you don't have a full loop? Let's say you have some random loop like this, and we have a wire here. Let this angle be theta. So let's say from here, so this will be your magnetic field. This will be your dl bar. If you remember in the last class, we have seen this. You can write the dl bar in polar coordinates. Any vector can be written in two perpendicular directions. So dr, r cap, radial direction, r d theta, theta cap, tangential direction. Hope you remember this. This was the last problem we did. And we know the magnetic field will be mu naught I 2 pi small r theta cap. It will be always tangential. So here r cap is perpendicular to theta cap. So now when you do this dot product integral v dot dl, only the theta cap dot theta cap will be remaining. Theta cap dot r cap will be 0. You get something interesting here. R cancels off. You get mu naught I by 2 pi integral d theta. there. So we get a result. Integral b dot dl. I'm not putting that circle, did you see? Because it's not a complete loop. Is theta by 2 pi into mu naught I. There, everyone. This is a partial Ampere's law actually. Instead of a loop, if you give me any random curve, if I try to calculate integral b dot dl, it depends only on the theta. It doesn't matter what is the shape of this curve. Now you can see if you put theta is equal to 2 pi, it becomes a complete loop. You get Ampere's law, isn't it? So I actually proved Ampere's law using Biot-Savart's law. But technically, what came first was Ampere's law. So experimentally, Ampere's law was first, and then came Biot-Savart's law. But yeah, Biot-Savart's law is more powerful. Is this derivation clear, everyone? Very useful statement. Matlab, you will see later on questions like, they will give you some partial loops and they'll ask you b dot dl. Most people will try to use Ampere's law and they'll not understand how to apply it. But if you know it depends only on theta, makes your life really easy. So look at this thing. So case one, if you make a full loop and if this is inside, so here your theta will be, you start from here and you go completely. Theta will be 2 pi. So now if you apply the formula integral b dot dl, you get mu naught I. This was your Biot-Savart's law. But what if the loop is, the current wire is outside? Now see what happens. From here, if you draw the tangents, when you go, let's say this point A to B, so when you go from A to B, you're going in this direction. So the angle theta will rotate this way. But when you come back from B to A, you're rotating in this direction. This will be minus theta. The angle is rotating in the opposite direction. So here integral d theta will be 0. Therefore, integral b dot dl due to outside wires will be 0. This was the reason when we did this formula here, look at this. B bar is due to everyone, but I is only due to the current crossing. Because the wires outside the loop will have integral b dot dl 0. So you're literally adding zeros to LHS, it won't matter. Didn't something like that happen in Gauss law? If you had a surface and if you have a charge Q outside, every line that enters will leave. Therefore, the flux is 0 due to the charges outside. That's when the Gauss law, if you see, the Q is the Q enclosed, whereas the E can be due to everyone. Is this making sense, everyone? Let's see a question on this. So let's say we have a wire here. This is L comma 0. This is L comma L. This is 2L comma 2L. And this is 3L comma 2L. Find integral b dot dl for A to B, for A to C, A to D. Get this? They'll just ask like this and leave it up. Matlab, it's not a loop. They'll just give one wire and they'll ask you what is integral b dot dl. When people say this, they think about Ampere's law, but there's no loop only here. So I can't do mu naught I crossing. Get this. So this is the formula you have to use. I don't care about the shape of the loop. What matters is the angle subtended by the ends. Mm, this was easy. So when you go from A to B, so you just join the ends, A and B. This angle is 45 degrees, isn't it? And when you go from A to D, this angle theta, tan theta will be opposite side 2 by 3. So yeah, so first case, integral B dot dl from A to B, the formula was theta by 2 pi mu naught I. Theta was 45 degrees, so 1/8 of mu naught I. So it doesn't matter actually what is the shape. You just take the two ends and get the angle. So here theta will be tan inverse 2 by 3. Clear? That's the advantage. Or else, you know what you would have done in this normally? Because this is the wire, this is the loop. You will say at a distance x, at length L, then you find the magnetic field here B, then you take dx here, then you integrate for each segment. You have to do all that stuff. But this will save you. Let's say we got a loop. This is an infinite wire. This is also infinite wire. This is also an infinite wire. So it's a big loop. This is making an angle theta. Just give me a minute. I'm just knocking the door. So this is wire one. Understand something here. This wire is infinity, but this distance is finite. This wire is infinity. This distance is also infinity, isn't it? Hope you're getting the difference. The wire, upper wire and the lower wire, both are not same distance. See here, the angle is theta. Here, the angle is 90. So this is wire one. This is wire two. This is wire three, and this is wire four. So find integral B dot dl over the loop for three cases due to all wires, due to wire one, due to wire 2. Get them. This is the loop. So on this loop, I want the magnetic field due to wire 2 dot dl ka integral due to wire 1 and due to all wires. There we are just playing with an Ampere's law. Integral b dot dl is mu naught, I think. First one was easy. What is integral b dot dl to all wires? That was a definition of Ampere's law, isn't it? Integral b dot dl due to all wires is mu naught I. Current crossing the loop. There's only one current crossing, which is mu naught I. That is straightforward. Getting it, but if you ask only due to wire 1, I have a problem. I can't use mu naught I because that B bar was due to everyone. So how do you define for the second one? For the second one, you just actually do the brute force. If you look at the wire, isn't this an infinite wire? So at this point here, look at the field. So this is theta, this is 90. Isn't this a finite wire ka formula? So here your magnetic field will be this way. DL also will be in the same direction. So how do you find the magnetic field? The finite wire ka formula mu naught I by 4 pi d sine theta plus sine 90. Here B bar is parallel to DL. So integral B dot DL will be mu naught I by 4 pi r 1 plus sine theta dl, and the angle between them is 0. Mu naught I by 4 pi r 1 plus sine theta integral dl, which will become 2 pi r. There, we just integrated this. Clear what we did? We took the field due to finite wire and we finished it off. Why can't I do this with the wire too? Look at the shape of wire 2. Wire 2 is like this. You're getting it. So if I try to use the infinite wire, I'll get the magnetic field in this direction, right? But your loop is in this direction, right? I cannot do the same thing for wire 2. For wire 2, the magnetic field and the loop are completely weird. Are you getting this? So how should I get for wire 2? What I did for wire 1, I can't do for wire 2. So how will we handle wire 2? We already know due to all wires. We know integral b dot dl due to all wires. b1 dot dl, b2 dot dl, b3 dot dl, and b4 dot dl. And if you observe here, this and this will be 0. Since wire 3 and wire 4 are at infinity, they don't have any magnetic field on the loop. That was the thing. The wire 3 and wire 4 are at infinite distance. They don't have any magnetic field there. Whereas wire 2 is at a finite distance. There will be a magnetic field. So if those two are 0, I know the total, which is mu naught I. I know due to wire 1, which is mu naught I by 2, 1 plus sine theta. That means the balance must be due to wire 2. So this is how you find for wire 2. There is no way to get wire 2 directly. Clear? For wire 1, the magnetic field and the loop ka length will be parallel, whereas wire 2, you cannot find. There is no direct way to figure it out. Is this clear, everyone? Yeah, this is how they can twist that Ampere's law and you can get questions of this sort. Any doubts on this step? You're getting now? How will the wire 2 will look like? For wire 2, the magnetic field will be that way. It will be concentric to the axis. But the loop is something else. So you can't do B dot DL for this. Because if you want to do B dot DL, you need magnetic field here. You need magnetic field here. I don't know how to do those things. That thing is in different plane. All clear with this? Ahana, Pushkal, clear? Saish, Ansh, Kush, clear with this? Vihan, Vignajit, Niharika. Next thing. So let's see the applications of this. So how do we use this? So I'll take a first one example. Like I said, if the shape is symmetrical, you can use this to find magnetic field. So I will take the infinite current wire, which I've already done. But let's see. How do we use this? The way we did in Gauss law. Step 1, assume a symmetrical Ampere loop. It should be symmetrical so that the magnetic field will be same at everywhere. Just like Gaussian surface, assume a symmetrical Gaussian surface. All right, such that all points have same magnetic field. Mod B bar, and the B bar must be parallel to DL bar because I want it to come out of that integral. Step 2, we'll use integral B dot DL is equal to mu naught I. if B is constant and if B dot dl is parallel, the B will come out of the integral. I can find the beta value. So let's see here. Step one, consider a symmetrical Ampere loop. For an infinite wire, the most symmetrical shape is a ring. All points on the ring are equidistant, right? So therefore, by symmetry, I can say the magnetic field will be also this way. The dl also will be this way. Then if I use the Ampere's law, integral B dot dl is equal to mu naught I current crossing. This will be integral B is parallel to dl here. So this will be mod B, mod dl cos 0. So on the LHS it will be always the same. The B will come out. You'll be stuck with integral mod dl. Mod dl is nothing but the circumference. Therefore, the magnetic field is mu naught I by 2 pi r. Isn't this the formula for infinite wire? We though did a big integration if you remember. We did finite wire, then we kept theta 1, theta 2, 90, and we did all that story there. So if the shape is symmetrical, Ampere's law will give you the answers pretty easily. But if it's a finite wire, this won't work. So both have their own advantages. This thing has a lot of limitations. It gives you answers, but there are a lot of conditions. Clear with this? There, this is the idea how we do. So we will do few more shapes. Now you guys try this. These shapes we didn't do in Biot-Savart's law also, which we couldn't do in Biot-Savart's, so they were little difficult. Infinite hollow cylinder. Just like, in Gauss law, we did infinite hollow shell, infinite बोल रहा हूँ, charged hollow shell. Infinite current carrying cylinder. So here the current is flowing on the surface. So if you look at the top view, this is how it looks. Current is coming out of the like this. And there is something more here. Listen. Remember last class we studied if you have two current wires parallel to each other, will they attract or repel? They attract each other. So parallel current wires attract each other. That means on this shell, every surface, every point is behaving like a parallel wire. They all attract each other. That means if you look at this, it's getting attracted, 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 attracted. This is getting attracted, 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 attracted. So this will lead to a kind of a compression. Because of this, the cylinder is under compression. This actually happens whenever you send current through a wire, the wires actually become compressed, they become more stiff. So if the current is under, because of the cylinder is in compression, but you're not letting it compress, so there'll be a pressure on the surface. So the first question, find the magnetic field as function of x. X is the distance from the axis. So find the magnetic field inside and outside. Second, find the magnetic pressure on the surface. Just like we have electrostatic pressure, that is due to the electrostatic charge repulsion, here there's a magnetic attraction. This is the third time you're encountering a pressure situation. Find the magnetic pressure. Just like electrostatic pressure, this thing also is similar, magnetic pressure. Get the first one, that is based on Ampere's law. Second is a more tricky one. If you remember how we derived in a hollow shell, it was the same theme actually. Did we do this? Here, this question, if you remember, we had a thin, hollow, charged shell. Sigma is the surface charge density. Find the electrostatic pressure. And you remember the result? Sigma square by 2 epsilon. Let's get this. The derivation is a little pain, but the final result, that's the easy way to remember. So if I just ask you find the magnetic fields, it will be still a mains level question. The moment I ask magnetic pressure, it becomes an advanced question. Try. I'll give you a minute or two. Let's get the pressure. Let's get the magnetic field first. Pressure, I'll help you out. Let's see the field part. Step 1, consider a Gaussian Ampere's law, Ampere loop. So for r less than r, so take a radius r. So integral v dot dl is mu naught I crossing. LHS will become b into 2 pi r. So LHS will always become b into 2 pi r. Right side is 0. There's no current only crossing through this, so b is 0. This thing will look similar to a hollow shell ka result. For outside, take a Ampere loop, a bigger one. LHS will be same thing. I'll just write down a few more times. Integral b dot dl is mu naught I. This will be b into 2 pi r. All the current is passing through the loop. There will be mu naught I. Therefore, the magnetic field outside will behave as if there is an infinite wire in the center. Isn't that how a hollow shell used to behave? The field outside a hollow shell is similar to having a point charge at the center. So if you try to plot the graph will look exactly like a hollow shell, B versus R. So these things we didn't do in Bio-Savart's law, everyone. So these things you need to know. These are also standard results. Increases and decreases. The field part is easy. Mostly they'll either ask you a graph or they ask you to calculate the values in mains. How do you find the pressure? Think, take a minute, 2 minutes on this. How do you find the pressure on the surface? Hmm. Let me show you a few things before jumping into the solving part. Should go back to the electrostatics once and check out all those things again. Let's say if I take the top view, this is the full cylinder, right? Consider a thin slice here. Okay. Consider a thin slice here. So this will be equal to this gap here plus this thing here. So if I add this plus this, I'll get a full cylinder. So exactly how am I taking the element here? The element will look like this, everyone. So you're taking a cylinder here. You're choosing a thin element like this. The length will be L. This will be, let's call it some dx, right? That will be the dx there. So are you able to visualize how I did this? I'll show you, see how it looks. If you ever peel a banana, remember it would become like this. Are you able to visualize now? So if you take a banana and if you peel that thing, if you see now, this is how this whole thing comes out, isn't it? Now we are able to visualize that shape, a thin rectangular strip. So we are taking an element like that. So the same thing, if you look at the top view, it looks like this. Now, if you consider 2 points here, point A and point B. So just now we saw the field at BA is 0. The field at B will be mu naught I by 2 pi r. Now you will see why am I doing this, why we need this. Because see, when you calculate force on a, if I ask you find the force on this, I should take the field due to the remaining part on this, isn't it? I'm not supposed to take the full field. You cannot take the field due to yourself on your own current wire, isn't it? If you remember, that was the same argument we had in that also. So if you take 2 points here, so this is A, this is B, this is A, and this is B. Again, remember, these are actually currents here. There are a lot of currents here. So all these currents are generating some kind of a magnetic field. So let's call this thing B1 and let's call this thing B1. This thing will create a magnetic field B2. I should take it in the reverse direction. So let's say this is giving B1, B2. So A and B are very close to each other. A and B are just inside and just outside. So technically there's no distance between them. Here the field will be B2 and here the field will be B2. So field at A will be due to B1 minus B2, but I know this is 0. So indirectly I proved B1 is equal to B2. It kind of makes sense, isn't it? Think about it. In electrostatics, the field due to a hollow shell is 0. If I make a small hole here, then the field due to the small hole and the field due to the remaining shell must be equal, right? Because the total is 0. Do you guys remember that? The same way here, the total is 0. That means that small hole, the small thing here, and this whole thing will create equal magnetic fields. And the magnetic field at B will be B1 plus B2, which is mu naught I by 2 pi r. Therefore, we get B1 is equal to B2 is equal to mu naught I by 4 pi r. Now, why we need to do all this story? So what we have literally found here is on this small slice, right? When I take the field, so on this small slice, The current is I. The magnetic field will be B. Now you tell me, this B will be due to what? This is not the total magnetic field. This magnetic field, this is a magnetic field. Is due to the remaining cylinder after removing the strip. On the thin strip. Are you getting the issue there? If I take the total magnetic field B, that magnetic field which we calculated here, mu naught I by 2 pi r, is due to full cylinder. Just to give an analogy, let's say if there are 100 particles here, okay? I am asking you find the force on the 100th particle. So when I ask you the force, you will take the force on the 100th particle due to the remaining 99, isn't it? You don't take your own force on yourself, isn't it? You're not supposed to include your own force on this thing. Generally, that would have been negligible. But here, the problem that happened was they became equal. That small piece is generating the same amount of field as the entire remaining cylinder. So that can't be neglected. It is a very huge difference. So if you don't do that and solve the question, you'll get double answer. Getting the answer which you will get, if you take the BS total, you'll get double the answer. So IDL cross B will be the force here. This will be your F. This is your force on the strip. And this is not the first time. We did the exact same thing in electrostatics, if you remember. Dekho, same story we did. We said take a full cylinder with a hollow shell. There are 2 points A and B. Field is E1, E1, E2, E2. Same story. Did you see? And then when I calculated the force, I did the same thing. Force on the small patch is charge on the patch into field due to the remaining shell. We did the same derivation there. Yeah, the terms are different, but the story was the same. And then we got sigma square by 2 epsilon. If I didn't do that, the answer would have been sigma square by epsilon, which would have been wrong. I hope you're able to relate both of them. It was the same thing. Great. So we got the force there. This was the length L. This was the dx. So what is the current on the strip? The current on the strip will be the total current I by circumference 2 pi r into width of the strip was dx. So force on the strip is I length magnetic field. And the pressure on the strip is force of the strip by area. So this will be I, L, B, and area will be L dx. Substitute all the values here. That will be I by 2 pi r. LL will cancel. Dx also will cancel. I end up with IB by 2 pi r. And B is nothing but mu naught I by 4 pi r. Mu naught I by 4 pi r. So we get mu naught I square by 4 pi 8 pi square r square. That's your pressure, everyone. If you have not taken that half ka thing, you would have got 4 pi square r square. That option will be there. Lot of work. But there is an easier way to remember this. I'll show you that. It's easy to remember this. There is a way to remember this in a much easier way, which actually we will see that term in the next chapter, EMI, but I'll show you that. But everyone got what we did. Why I had to do this much story here? Normally we could have neglected because it is very small. Because of a hollow shell, it happened. It became so big that the both became equal. So how do we remember this? Let's see the electrostatics result. If you remember the electrostatics result, plus Q, radius R. The field on the surface was Q by 4 pi epsilon R square, which is nothing but sigma by epsilon. Then we got pressure on the surface was sigma square by 2 epsilon. Multiply and divide by epsilon. This will become sigma by epsilon square. This is half epsilon E square. What is this term called? What is half epsilon E square? Capacitors में क्या था? Energy density, right, Purvaja? This is electric energy density. This is the amount of energy stored per unit volume. There. So, in case you forgot about pressure, remember the energy density ka formula. That is only pressure. Getting it? Now the same story I can do here also. So B on the surface is mu naught I by 2 pi r. Here the pressure ka formula will be mu naught I square 8 pi square r square. So this will be 1 mu naught. This will become mu naught I by 2 pi r ka whole square. That will become 1 by 2 mu naught B surface ka square. So in the next chapter we will study, this is nothing but magnetic energy density. Even magnetic field is a form of energy. This is the amount of energy stored in the form of magnetic field per unit volume. Do remember this thing. You can skip the integration. Saves you a lot of time in the exam. But only for hollow shells. Clear? Any doubts on this? So you can remember that with the energy density formula. Half epsilon E square, you'll get 1 by 2 mu naught B square. See the relation, they look same actually. Half. E ka place mein B is there. Epsilon ka place mein 1 by mu naught is there. Every time you saw epsilon and mu naught will be numerator denominator. They'll be always reversed. Take a small break. Come back by 9:39. Any doubts so far? Chalo, come back in 5 minutes. There we have an infinite solid cylinder. Find B of x. Find pressure as function of x. Same thing. Now there will be a pressure inside the cylinder. Remember, we did this thing also in electrostatics. Solid sphere inside there is a pressure. Let's get this thing. So we have an infinite solid cylinder carrying current uniformly. Find the magnetic field inside and the magnetic pressure. Get the field inside. Field is easy. Let's say. Same thing. Consider up to R. So for R less than R, this side will be integral B dot dl is mu naught I. So this will be P into 2 pi R. This will be mu naught current density into pi small r square. So we get mu naught J small r by 2. Right? So this is proportional to R. It's a linear function. Or you want to write in terms of current also. That would be mu naught I by 2 pi r square into small r. For r greater than r, this will be again b into 2 pi r. It behaves like an infinite wire at the center. Yes, for the hollow and the solid, it behaves like an infinite wire at the center. So if you try to plot the graph, it kind of looks like solid sphere ka result in electrostatics. It will be a linear function and then decays. Clear? What about the pressure? That is the main question. Right, I'll give you a minute or two. Let's see. Again, how do we choose an element? Keep trying, keep trying. By the time I explain everything and start, you'll still get another 2 minutes. So we take an element like this from the center at a distance x. This is how it will look. So if I exaggerate this is a shape. This will be dx. This will be x d theta. This will be length. Current is flowing here, right? This is the current I. How is the magnetic field? Magnetic field also will be something of this sort. The force will be this way. So df will be ILB. I will be J into area of the cross section, which is x d theta into dx. Length, and the magnetic field is mu naught J x by 2. We derived this thing just now. Here you won't have that problem because the magnetic field with this thin wire is negligible in comparison. Previously, we had to take because both were equal. This is the force. Now, if you take this strip, if you look at the forces, remember this strip is being pushed from both the sides. So pressure will be P plus dP into area. This side the pressure will be P into area, and this will be dF. So we always assume the pressure is increasing with x. That is a mathematical way of doing it. So from here, when you do this, you will end up with dP is equal to minus dF by area. The minus indicates pressure is not increasing, it is decreasing. The science will take care of it. And do you remember what is the pressure on the open surface? The pressure on the open surface will be always zero. Because see, there's nothing pushing you from outside, so there's no pressure on the surface. Everything is getting compressed. So the center will experience maximum pressure. And this is not the first time. We discussed this term multiple times, if you remember. I think first time, we discussed that was in circular motion. Remember, there are no forces here. The open ends will always have zero tension. You remember this term? Because there is no one here to push or pull here. There can't be any tension there. If there is a tension there, whom are you pulling? There's a vacuum on the outside. So pressure on the outer surface is zero. It's not an air pressure or anything. Because of the attraction, everything is pulling in. You getting this? So when you try to integrate this term, so we'll get df will be minus that weird term there, mu naught j square L x square d theta dx by 2, and area, which area we are taking here? If you take this area, which is L into x d theta. So the d theta and L, this thing goes off. We get mu naught j square x dx by 2. Yeah, so integrate this. Limits, this will go from r to x, and this will go from 0 to p. Be careful, pressure is 0 at x is equal to r. So we get pressure is equal to mu naught j square by 4 r square minus x square. This is the pressure on the surface. Do you guys remember solid sphere में result क्या था? Rho square by 6 epsilon r square minus x square. This one. If you remember, here also we did the same story. देखा element? We took a small element and we did the same statement here. Pressure on the outer surface is zero. Free hands are zero tension. The theme was the same. There it was electrostatic pressure. Here it is magnetic pressure. I can do the same thing in gravitation also. So in total, you will get fluid ka pressure, gravitational pressure, magnetic pressure, electrostatic pressure, and field radiation pressure in modern physics. Total, there are 5 times you'll get pressure. Technically, there is no difference between them. All of them, will work on projected area. Everything you did in pressures will work. There's no difference between them mathematically. Stay with us. Any doubts on the elements? Anything that you're not clear? You should know how to do these things, because next question, they can ask something of that sort. We'll not do pressure, but let's find this thing. What if you have a cylinder where your current is non-uniform? Symmetrical, but non-uniform. Let's say we have a current density J is equal to J naught 1 minus x by r for x less than r. Plot the magnetic field versus x coordinate. I mean, look at how is the current. At the center, the current is maximum. As you go out, the current decreases and becomes zero. Current decreases and becomes zero. Plot the magnetic field versus x-axis. X is the distance from axis. So here they can ask you, here also find the pressure. Idea is the same. But this is a pretty good question. If I ask you to plot the graph, that would be a pretty good advanced and maybe a single choice question. Let's get this. All the questions we are doing today, make sure to definitely solve them. Like, all of them are advanced types. One more minute. How will you draw the graph? Let's see. Roots. Who the hell cares about roots, right? No, it's not a max class. First of all, see, before jumping into the Ampere's law, you need to figure out something. If you take a radius r, the current itself is changing here. So at a distance x, take a thin ring. You need to first get the current within this small r. So the current here, di, will be j into 2 pi x dx. So this is I, this is the current up to r, will be integral j naught 2 pi 1 minus x by r. So that will become x dx minus x square dx by r. This will go from 0 to r. This will be 2 pi j naught r square by 2 minus r cube by 3r. I hope everyone got this. This is the current up to small r. I net current, the total, will be when x is equal to r is equal to capital R. When you keep r is equal to capital R, that will become pi j naught by r square by 6. That is your total current flowing in the cylinder. 6, no, 3. Clear with this? That's the total current in the cylinder. Now let's use Ampere's law. So for r less than r, LHS will become p into 2 pi r. This will become mu naught I, where I is nothing but this guy. Mu naught I will be 2 pi j naught r square by 2 minus r cube by 3r by 2 pi small r. If I do maximum minima here, dB by dr equal to 0, I'll get half minus 2r by 3r is equal to 0. We get r is equal to 3r by 4. So this function will peak at 3r by 4. For r greater than r, this will be b into 2 pi r, which will be mu into I net. So this thing will just be like an infinite wire outside. Mu into I net by 2 pi r. I'll give it like this. So if you try to plot the graph, agreed, it's a parabola, but it won't complete a full parabola. It will take a turn. This is still r. The peak value will occur at 3r by 4. So the magnetic field maximum is not on the surface, it is actually inside. Once you get till here, then the graph becomes 1 by r function. This will be your Vmax. Clear with this? That was the reason we need to do that maximum minima. We need to know where is the maximum value. The surface need not have a maximum field in this case. All clear with this? There. That's why the graph was important. Any doubts on this? So every time you won't get uniform. If you get a non-uniform, these questions, right? This hollow cylinder and solid cylinder and this thing, you can't do this with Biot-Savart's law. Ampere's law will save you there. So if you till now, if you see all the shapes, finite wire, arc, field on the axial line for a ring, solenoid, infinite plate, hollow cylinder, solid cylinder. Let's see one more. This is another standard result which you should definitely remember. If you have a cylinder with a cavity, anyone remember the result for a solid sphere with a cavity का result in electrostatics? This is a solid cylinder with cylindrical cavity. Rho by 3 epsilon O dash bar. याद है? This is O dash. This is O. J is the current density. Find the magnetic field inside the cavity. Answer will come in terms of J, O, and O dash. So if you look at this in the top view, this is the cavity. This is O and this is O dash. So these kind of cavity problems, right, you can see in gravitation, electrostatics, and magnetism. And you can, even if you don't know the result, you can guess, right? Field inside will be constant. We proved that in electrostatics. Let's get this. If you remember, right, whenever you see a cavity, what is the technique? First time you encountered cavities was what? In center of mass, then rotational mechanics, then electrostatics, gravitation. You always take the full cylinder. From there, subtract the cavity ka cylinder. Then whatever is left out is the result you are looking for. Isn't that how we do? So this is O. This is O dash. This is some random point P. So this is O dash. This is P. This is O. This is P. We know the field inside a solid cylinder is mu naught J by 2 OP bar, the magnitude, and the vector is perpendicular to OP bar. So this is how the field is. So the field depends on the distance OP bar, but it is perpendicular to the R bar vector. This is B1. Similarly here, if you take B2, This is also mu naught J by 2. It depends on the magnitude O dash P bar perpendicular to O dash P bar. So therefore, the field inside the cavity here will be simply B1 minus B2. You can clearly see there, if you subtract OP bar minus O dash P bar, this can be written as OP bar plus PO dash bar, which becomes OO dash bar. So you get a result mu naught J by 2 magnitude OO dash. The direction is perpendicular to OO dash bar. Clear with the result. So in electrostatics, it was rho by 3 epsilon. Here it is mu naught J by 2. So the result, the picture would look like this. This was O. This was O dash. So your field will be perpendicular to this line. And it will be constant. Field won't be along the line of O dash. If it's a mains level question, they'll simply ask you the field inside is in which direction, is it constant, changing, all that kind of stuff. Clear with this? So you see a cavity, this is the technique. You take the full, subtract the cavity, whatever remaining is the answer. This is what we have been doing from the beginning whenever you encountered a cavity. Any doubts on this? There, these are the main shapes and everything. After this, we have the infinite current sheet, which I've already derived using the Biot-Savart's law. But let's see how they will use Ampere's law to derive. Mostly, for the HSE, they might ask you the derivation, or if at all they mess up the current or something, you should know, because Biot-Savart's law will be very painful then. So if you have an infinite current sheet, so first of all, it is always about choosing a proper Ampere loop. So if I take this point here, so here the field will be this way. Here the field will be this way. Symmetrically, if I choose one more point here the field will be this way. Here the field will be this way. So here we can see by symmetry, for every two wires, the field will be in the horizontal direction. If you remember this, we proved even there also. The field will be always parallel to the surface. So this is the first step. Matlab, we proved the field is parallel for any two, because there's an infinity, every point is a midpoint. Next thing, consider an Ampere loop. So here the magnetic field B will be this way. So here B is this way. Here B is this way. And if you look at DL here, this will be DL. Here DL is perpendicular. DL is perpendicular. Again, DL is parallel. DL is perpendicular. So the B and DL are parallel only on the horizontal thing. And let the length be L. So when you do integral B dot DL is equal to mu naught I, you can clearly see A to B may it works, B to C it will be 0, C to D it works, and D to A it is 0. This will become 2 times BL is equal to mu naught. K is the current per unit width. So here width is L and this will be KL. LL gets cancelled, we get B is equal to mu naught K by 2. Remember the result? For BC and AD, B is perpendicular to DL. For AB and CD, B is parallel to DL. There. The proof was so easy, right? There was no big integration, nothing. That is the advantage of Ampere law. It really gives you the answer pretty neatly and fast. But the headache, the moment the shape is not symmetrical or not infinity, you're gone. So it has its own limitations. So it works under certain conditions. Clear with this? The next one, infinite solenoid. So before jumping into the solenoid, here also we need to see something. So in the entire solenoid, if you take any two rings symmetrically, so see here, if this is the magnetic field B, if this is the magnetic field B, you will notice the field is horizontal here. But if you go too far, so here the B is this way, here the B is upward. So basically the fields cancel out outside. So here the B net is 0. So that means if you take a solenoid, right? So if you take a lot of turns like that, just should be 2. But if you take an infinite turns like this, there'll be always one other loop which will cancel the horizontal component and so on. So outside the solenoid, B is 0. Within the solenoid, the field length will be always horizontal. That we prove by symmetry. We say if we take two loops in the middle, they'll add up and outside they'll cancel out. N is the number of turns per unit length. Then what do we do? Consider an Ampere loop. So in this loop, if you observe, we have currents are coming out of this loop. Remember, mu naught I is the current crossing the loop. Let this be L. Same story. Here is the magnetic field is 0 outside. Let me show it in the next page. Inside there is a magnetic field. Here it is perpendicular to the DL. Here B is 0. Here B is 0. Here B is 0. Here B is perpendicular to DL. Let the length be L. So these are all the currents which are coming out. So there are N turns which are crossing this. Integral B dot DL is mu naught I crossing. So I is the total number of times the current crosses the loop. You're getting how it is? If you take a loop here, every time the current is just coming out, right? See, the current goes out, it goes out of the loop, again it enters. The loops are continuously crossing. So this will be B into L because only this length will have B dot DL. This will be mu naught. The total number of turns are N into small l is equal to Y. L cancels, we get B is equal to mu naught I. Can you see? The result comes out pretty neatly. Yeah, these are the other two shapes, the infinite wire and infinite solenoid, which we have derived in Biot-Savart's law, but yeah, this is an easy way. Definitely, you need to remember this result. So if you take an infinite solenoid, just like capacitor ka parallel plates is a result, infinite solenoid is also a result. It's important. Later on in the next chapter, we will see. Parallel plates are called a capacitor, infinite sheets. A solenoid is called an inductor. This will be our next device: resistance, capacitor, inductor. So an infinite solenoid doesn't exist. So anything, length is much, much greater than radius is called as infinite solenoid. So inside an infinite solenoid, the field lines are parallel and the value is equal to mu naught Ni. But what if you take a semi-infinite solenoid? So one side is infinity, the other side is an open end, which you can see. Now that means, tell me one thing. If I take two semi-infinite solenoids and I join them, then I'll get an infinite solenoid. That means at this open end, the field lines, if you look at them, they will not be parallel. They will be going off like this. But you're saying if I join two semi-infinite solenoids, I should get back mu naught Ni. That means each one is providing a component Bx. So the fields are not equal, but the horizontal components will be equal. Bx will be mu naught Ni by 2. Quite a useful result, right? So if you look at the open end, the magnetic field at each point is different. But all these magnetic fields, if you take the horizontal components, they'll be equal. Because when I join two semi-infinite wires, I should get mu naught Ni back. Remember that result? We're going to need that in the next class. All points on the open end have same horizontal component of magnetic field. The magnetic field is different at different points, but the horizontal component is same. Clear with this? Next one. So let's say we have an infinite solenoid. Now you took this and then you did rewounded it. To half the radius. Again, remember it is tightly wound. I am giving spaces, but technically there will be no spaces. And L you can take it as much, much greater than R. So you can use that infinite formula. So the solenoid becomes R by 2. If you send the same current, find the ratio of magnetic field inside and find the ratio of magnetic moment, NIA. मेरे बहन। It's to 4, 4 is to 1. Listen. So when you made the radius half, the length of the wire has to remain same. So this will become 12. And the turns will become 2n. The number of turns per unit length, small n, will not change. This will remain constant, isn't it? Think about it. Number of turns will depend on what? Number of turns will depend on the thickness of the wire, isn't it? For example, let's say I have a wire, okay, whose thickness is d, right? So let's say thickness is 1 centimeter. Now you tell me, in 1 meter ka thing, how many wires can I fit in? 100. Suppose if I make the radius smaller, again, remember which radius? I'm not talking about the radius of the wire. I'm making about radius of the loop. That means if I make this smaller, but still this is 1 meter, how many wires can I fit in? Still 100, right? How many wires can fit inside will depend on the thickness of the wire. It doesn't depend on the radius of the loop. Are you getting it? Think of like this. Look at your 4 fingers. If you make it like this, can you see this thing? Aren't these like loops? If you take your fingers and make it like this, are they like loops, right? So each finger is occupying this much space, isn't it? If I make this fist big or small, the area they occupy will be only 4, no? Whether I make it big or small, there'll be always 4 loops only within this area, isn't it? So by rewinding, number of turns will never change. Are you getting this? So mathematically, right, this is what it looks like. Suppose if you have the turns like whatever, it's like this. Let's say the width of the wire is d. You can call this diameter of the wire. This is not the loop. So this is 1 turn, isn't it? So what is small n? Small n is 1 turn in how much distance? Small d, na? Where d is the diameter of the wire. Are you getting this? So here small n, number of turns per unit length, does not depend on the radius of the loop, or it depends only on the width of the wire. So it doesn't matter how many times I rewind it or do anything, that thing doesn't change. So if I use a thinner wire, now that will be a different question. If the thickness of the wire is made half, then you can put more loops into that same space, isn't it? So A will be B is equal to mu naught Ni. Mu didn't change, N didn't change, nothing changed. So B1 by B2 is 1. Second thing, magnetic moment will be number of turns. This is different. Capital N is the total number of turns, area. So mu1 by mu2, number of turns N I pi R square. Here number of turns became 2n I, this became R by 2 square. This will be 2:1. Clear with this? Got it? There. So that is one way of asking. Let's see one more. So we have an infinite current carrying plate. It has some thickness also. So this side is infinity. This d is the width or thickness. B is the breaking stress. K is the current per unit width. Width is which one? This will be width, na? That will be width. You're getting it? Thickness is different, width is different, so be careful. This is thickness. This is width. Current per unit width. The current is flowing like this, na? B is your breaking stress. So something happens. If I keep sending more and more current, the plate breaks. Find the maximum value of K so that the infinite plate doesn't break. Yeah, I combined magnetic field with this thing elasticity. What is the catch? Why the hell will the plate break? That is the main thing. Why will the plate break? If that is the only thing, because solving is easy. Who is creating the force on the plate to break? So when you have the plate, do you have the magnetic field? The plate is generating its magnetic field, right? Which direction? Current is going in. So field will be this way. Field will be parallel to the plate that way. Now, if you take a small width here, dx, in this part, there is a current flowing here. I dl cross B will give you a force. So the plate is generating a magnetic field because of that its own magnetic field. Getting it? Now this magnetic field due to the other ones is creating a force on that plate, which is pushing it down. So if you take this thin cross section, this thing looks like a Kit Kat ka bar. So basically on this surfaces, you're getting a shearing force, isn't it? This will be the tension and this will be the tension. And this guy is pushing down, isn't it? Are you able to visualize how it is? Take a Kit Kat and you're trying to push the middle one down. It's like this thing. See, if you're looking at my fingers now, my four fingers are there, these are like plates. Someone is trying to push the middle one like inside. So you're getting it? It's like this. If you push it from here, it goes off like this now. You're able to see how it is? If you take your four fingers and try to push one like this, so they will separate out like this, isn't it? You're trying to push out one. So the whole thing is being pushed down. So this is pushing it down. So this is actually a shearing stress. So there will be a tension parallel to the surface there. So this should be this is a breaking stress, which is shearing stress basically. So you should take this area, which will be how much? This will be dx. This will be length L and W. The plate is being pushed down. So basically, each section is being pushed down. Given the length also, okay? This was D. This was dx. That was length L. What is force? Force will be I length B. I is nothing but K dx. Length L and B. So here we get 2 times tension is equal to force. So tension will be F by 2. So breaking stress will be, this will be actually shearing stress. Shearing ka breaking stress. So I should add it here. Breaking shear stress. That will be the tension T by area. Which area? That will be D into L. I'll be stuck with the dx actually. I thought the dx will cancel off. T will be F by 2, which is K dx L B by 2. What is this B actually? This B is also mu naught K by 2. Tension by area will be L into D. LL got cancelled. Mu naught K square by 4D dx. Something went wrong. So it is depending on how much thickness I took. That is not right. The force is acting down only, right? L didn't come. That is great. I should have given this is breaking stress per unit width or per unit. I need to change that data point there. Breaking stress per unit width. Then that side also will get a dx. This will cancel off. Then we'll get the answer there. Let me see. I'll think about this thing. We need to get the data right. But anyways, got the idea, right? There is a chance the plate will break. That was the thing I was trying to show. I just made up the question on the spot. I think that's where data didn't fit. Anyways, but there, even that plate, right, will have a kind of force on it. The last thing is a toroid. We just have a result there. We don't have any questions also on this. So do remember, a toroid looks like a donut. Technically, the edges should be smooth. I'm unable to draw it properly, so I'm putting it flat edges. So toroid is nothing but a solenoid, which is made into you just connect it round and finish it off. Make it like a loop. It's like a snake eating its own tail. Sometimes now when snake gets angry, right, it thinks its tail is the enemy and it starts biting its own tail. So there's a thing like this. When a person is angry, right, that's what we also do. We start behaving very weirdly. Anger turns you into a different person. This is the total turns. So just remember the result. I have not seen any questions on this so far. So here the field will be only inside, which is mu naught ni by 2 pi small r. There'll be no field outside and inside, meaning from 0 to a there'll be no field, there'll be no field outside B. There. Yeah, solenoid connected its own end. That is the last shape that we have. So total shapes that we saw were finite wire, arc, field on the axial line, infinite sheet, infinite solenoid, hollow cylinder, solid cylinder, toroid, field inside a cavity, something like 7 to 8 shapes. So do remember this. So with that, we are done with the chapter also. So do start solving. After this, we have bar magnets and all, but that is primarily mostly on the main side. So that we will see in the end because there is a bunch of another 12 formulas. So we'll do that in the later on. The next chapter will be electromagnetic induction. We will start off on Monday. So in mechanics, rotation was like the thing, right? So same way in entire electromagnetism, EMI is the thing. It has every damn thing will come up again. You will see rotational mechanics, you will see electrostatics, that and this, everything pops up. Pretty interesting chapter. Pretty good weightage also. So if you see in physics now, there are certain topics which are like advanced perspective, they're very important. One is electromagnetic induction, AC circuits, rotational mechanics, right? Modern physics, wave optics. So there are certain things like this. So anyway, so we'll catch up on Monday. We'll continue from there, right? And there's a recent test you saw. It was easy test, right? There were a few corrections. I got it done. Check it out. So the next test is advanced test, ray optics. So do prepare and go for that. It won't be as easy as this. Okay, with that, we'll wrap up for that. I'll see you guys again on Monday, 8:30 as usual. So any doubts, anything, please stay back or else you're free to leave.